This is the second part of the 8th lesson in heat transfer. The 8th lesson is looking at problems that can be categorized as steady state, one-dimensional, and in which properties are a constant, and there is thermal energy generation. In this second part of the lesson, we will look at how to do a differential analysis. In the first part of the lesson, we saw that we need a new form of analysis for categories of problems such as those that include thermal energy generation, because the thermal circuit model does not apply. By the end of this lesson, you should be able to explain what the goal of a differential analysis is. You should also be able to apply a differential analysis to determine the equation for the temperature distribution in a medium in which there is conduction heat transfer. On with the lesson. The goal of a differential analysis is always to find an equation for the variation of temperature in space. If the problem is transient or unsteady, then the equation also includes the variation of temperature in time. Differential analysis can also be applied in other engineering disciplines, where the goal is to find the distribution of some other physical variable than temperature in space and in time. For example, in fluid mechanics, one may apply a differential analysis to determine the distribution of pressure within a liquid. Because heat transfer is focused on thermal energy, the goal is always to find a distribution of temperature. It is important that you keep this goal in mind. We will use this temperature distribution to answer relevant questions and also to analyze the rates of heat transfer by conduction. Let's now look at the steps of a differential analysis. The first step of a differential analysis is always to define an appropriate differential control volume and sketch it. There are certain properties of the control volume to keep in mind as you create your sketch. The control volume should be infinitesimal in size in the direction of the temperature gradient. This means that the control volume has a very, very small extent in this direction. The control volume should be finite in all other directions, encompassing the entirety of the domain of the problem. All thermal energy flows across the surfaces should be drawn and labeled on the differential control volume. Finally, all thermal energy generation should also be drawn and labeled. The second step is to apply the heat transfer energy balance equation to relate the processes that are depicted in the differential control volume. The third step is to apply the Taylor series expansion to develop an expression for the net rate of heat transfer by conduction. In the fourth step, one substitutes in the rate equations for heat transfer. For problems that involve also convection, one would substitute Newton's law of cooling. For problems that involve thermal radiation, one would substitute an appropriate equation for the net radiative flux. In the fifth step, simplify the resulting differential equation and solve it to obtain the homogeneous solution for the temperature. This equation governs the temperature inside of the control volume. In the sixth step, develop equations for the boundary conditions. These are the conditions at the surfaces of the control volume. Finally, one combines the homogeneous solution and the boundary conditions to obtain the particular solution to the problem. We will now apply these steps to the example problem that was introduced in the first part of the lesson. As a reminder, here is a sketch of the example problem that we are considering. We are working on the example of a planar nuclear fuel element. Due to nuclear decay, thermal energy is generated within the element. We want to answer the question, what is the temperature on the inside of the fuel element in steady state operation? And in particular, what is the maximum temperature? This is an important question because an engineer would need to ensure that the fuel element remains at a safe operating temperature at all times. The first step of the differential analysis to determine the temperature distribution is to sketch a differential control volume. Here I have drawn the differential control volume on the original problem sketch. Because the temperature gradient is in the x direction, the control volume must have an infinitesimal size in that direction. Even though I have drawn the control volume so that it looks like it has a finite size, we must imagine that this is actually an incredibly thin slice, as thin as one might slice it if we were to cut the wall with a knife. The control volume can be finite in all other directions, and so the control volume encompasses the entire cross-section of the wall at this particular location inside of the wall X. Here I have redrawn the control volume larger to make it easier to label thermal energy generation and rates of heat transfer across the surfaces. The first step is to make sure that we are aware and cognizant of the geometry of the control volume. The control volume has a differential thickness. We denote that with a dx. That is a reminder that the element is very, very thin. The face of the control volume has an area that we can set equal to 1 square meter. We are thus analyzing a square meter of the fuel element. Because the area is a square meter and the thickness is dx, the volume of this element is equal to the area times its thickness. There is thermal energy generated within this differential control volume due to the nuclear decay of the material. We can denote the rate of energy generation by the volumetric rate of generation times the volume of the control element. Recall that the units on the variable Q with 3 primes is watt per cubic meter, and the units on the volume are cubic meter. The product of these two gives us watts, which is a rate of energy generation. Heat transfer occurs across the faces of the control element by conduction, because the control element is on the inside of the fuel element. There is conduction heat transfer from the inside out. Heat transfer thus transfers in across the left face of the control volume and transfers out across the right face. These rates of heat transfer need not be equal to one another, and so we have denoted that they are different due to the very small difference in spatial coordinate. The second step is to apply the heat transfer energy balance to relate the processes that we have identified in the control volume. This is the heat transfer energy balance equation. Because the problem is steady state, there is no energy storage term. We can set it equal to 0. There is a heat transfer in. It is the Q conduction at the face at X. There is a heat transfer out. It is the conduction heat transfer at the X plus dx face. And there is thermal energy generation. We now substitute these terms into the heat transfer energy balance equation. In the third step, we apply the Taylor series expansion to develop an expression of the net rate of heat transfer by conduction. The net rate of heat transfer will combine the conduction heat transfer in and the conduction heat transfer out into a single term. Since the control volume is very thin, we can approximate the function for the conduction heat transfer as a line. We thus say that the conduction heat transfer at the X plus dx face is equal to the value of the conduction heat transfer at the X face plus the slope of the line, that is the conduction heat transfer function, times the distance over which that function changes. We are essentially extrapolating the conduction heat transfer at the X face to the x plus dx face. Substituting this result, which comes from the Taylor series expansion, neglecting higher order terms, back into the heat transfer energy balance equation, allows us to simplify the equation. Here I have made the substitution. We can now simplify. The Q conduction x term drops out of the equation, and we are left over with minus the derivative of Q conduction times the differential extent of the volume plus the volumetric rate of energy generation times the differential volume size. The fourth step of the differential analysis is to substitute in the rate equations for heat transfer. Here is the equation that we have from our heat transfer energy balance equation with the Taylor series expansion used to simplify the conduction heat transfer terms to provide the net rate of heat transfer by conduction. We now need to substitute in the rate equation for conduction heat transfer. The rate equation for conduction heat transfer is Fourier's law. Fourier's law provides an expression for the heat flux by conduction heat transfer. Our heat transfer energy balance equation includes an expression for the rate of heat transfer. We thus must multiply the flux by the appropriate heat transfer area. Fourier's law is -1 times the thermal conductivity times the slope of the temperature distribution. We now substitute this result into our heat transfer energy balance equation. I have simply substituted in for the conduction heat transfer term. Now that we have substituted in the rate equations for all of the heat transfers, we can simplify the resulting differential equation and solve it to obtain the homogeneous solution for the temperature. Note that because the thermal conductivity is a constant and does not depend on position x and be factored out of the differential. Similarly, the cross-sectional area, the area that is perpendicular to the direction of conduction heat transfer, is also a constant in this problem and can be factored out of the differential. Note now that we can divide this equation by the term A times d sub x. Also note that the two negative ones multiply together to become a positive. The resulting differential equation is as follows. If we solve this for the derivative term, we see that we have an ordinary differential equation for the dependent variable t, the temperature of the domain, as a function of the independent variable x, the position. We now solve this ordinary differential equation. It is separable. We can separate variables and integrate both sides. First, we move the d sub x to the right-hand side, leaving the derivative of the temperature derivative on the left. The integral of dtx is simply the variable itself. On the right-hand side, because the volumetric thermal energy generation is uniform and the thermal conductivity is a constant, this term can be pulled out of the integral, such that the integral is simply that of d sub x. As a result, the integration is simply x, and we are left over with an equation for the temperature gradient as a function of position in the wall. There is a constant of integration left over, since we did indefinite integration in this step, rather than definite integration. We can separate variables one more time and integrate again. Here I've moved dx to the right-hand side of the equation and integrated, and also integrated the left. Integrating the right-hand side, we have an integral of x dx, because again, the q triple prime divided by k is a constant and can be pulled out of the integral. The integral of x dx is x squared divided by 2. We also are integrating the constant c1. We are left over with c1 times x, and we have a second constant of integration from our second integration step. This is the homogeneous solution for the temperature within the volume. It applies to any planar volume in which there is a uniform generation of thermal energy and a constant thermal conductivity. In the sixth step of the differential analysis, we develop equations for the boundary conditions that exist at the surfaces of the domain that we are analyzing. At x equals 0, we have already shown in the first part of the lesson that the slope of the temperature gradient is 0. This is due to the symmetry of the problem. The boundary condition thus becomes that the slope is equal to 0 at this location. At x equal L, the surface of the fuel element, we have assumed that the cooling water flow maintains the temperature at a temperature T sub S. This becomes the second boundary condition. These are our two boundary condition equations, one applying at x equals 0, the other applying at x equal L. In the final step of the differential analysis, we combine the homogeneous solution and the boundary condition equations to obtain the particular solution. I have relisted the homogeneous solution and the boundary condition equations here for reference. Note that I consider the homogeneous solution both that for the temperature itself and the derivative of temperature. We obtain these from our two integrations. Those are two equations in our set. The third and fourth equations are our boundary conditions. The goal is to eliminate the constants c sub 1 and c sub 2. By taking equation 4 and putting it into equation 2, we can find out the value of c sub 1 easily. That is because our boundary condition states that at x equals 0, the gradient is 0. Substituting x equals 0 into equation 2, we have that q triple prime over k times negative 1 times 0 plus c1 must equal 0. This result tells us that the first constant in this particular problem must be 0. If we take equation 3 and substitute it into equation 1, we have that the temperature at x equal L is equal to Ts. We then substitute x equal L into equation 1. We have already identified that the constant C1 is equal to a 0. The second term thus drops out. Solving this equation for C2 shows that the second constant is given by the following grouping of terms. We now take our constants C1 and C2 and substitute them back into the homogeneous solution to obtain the particular solution. We can factor out the common q triple prime over 2k term to obtain our particular solution. This is the equation that allows us to calculate the temperature at any location within the fuel element. Let's now check our guesses for the temperature distribution within the fuel element that we made in the first part of the lesson. Here I have used a computer in order to create a graph of this temperature solution. I have plotted a new grouping of terms to make the problem more. To generate this plot, I have multiplied both sides of the equation by 2k and divided both sides of the equation by the volumetric thermal energy generation rate. This allows me to establish conditions for the curve with two parameters: the length of the fuel element, the half thickness of the fuel element, and a value for this 2k Ts over q triple prime parameter, which I have denoted as 0.1 meter. Note that the temperature distribution is parabolic. It goes to the x squared. The maximum temperature is at the center line. This is the location of symmetry. Did your sketch look at all like this one? You might fix your original sketch now. Isn't it incredible that by simply combining a statement of the conservation of energy and a statement for Fourier's law for conduction heat transfer, we were able to identify that the temperature distribution in this fuel element is parabolic. In the next part of the lesson, we will analyze this result a little further.